We made it finally time to talk about the definite integral. All the integrals we've been talking about so far, the antiderivative, that's called the indefinite integral. It's the antiderivative and you put a plus c at the end. As far as we're concerned today, the definite integral is something completely different, totally different from the indefinite integral. It turns out there is a deep and abiding relationship between the two of them, which is why they're both called integral. But for now, we're just going to talk about the definite integral. They're not going to tie together until a few times from now. Anyway, the definite integral, it represents the area under the curve of a function. For example, let's say this is my favorite parabola, y equals x squared. And let's imagine I would like to look over at x equal 1, which also has y equal 1, and consider this region down here. We refer to this area as the area under the curve. It is the area between the curve and the x-axis, all right? And this is what the definite integral measures. It's just that area. It has some area, right? What is the area there? I don't know. I mean, I'm sure in your youth you learned a bunch of formulas for finding the area of various shapes, but this is probably not one of those shapes that you know the area of. This is well, it's got two straight sides, but the third side is like the shape of a parabola. But there is an area. I mean, that's a real shape, so it does have an area. It turns out, I happen to know the answer here. This area is 1/3. Very strange, but true fact. The area under this parabola, y equals x squared, is 1/3. I don't know what you were expecting it to be, but if you ask me, I wasn't really expecting it to be such a nice number like that. The fact that it is such a nice number should suggest to you that maybe there's some kind of weird trick that you can use to figure out this number, and it ends up being not so hard to do because the answer ends up being not so complicated. It turns out it is not so hard to do if you know all about the definite integral. But let me just write sort of how we're going to write this. I'm talking about the area under the curve, of course, between the x values of 0 and 1. This would be written in this way. Integral from 0 to 1. You put these little numbers next to the integral sign. This means the area as I go from x equals 0 up to x equal 1 of the function x squared. And then you put a dx. This is just so that it looks like the indefinite integral. Only got these two little numbers here. All right, and what this means is the area under the curve of this function between these two x values. And in this example, that area is equal to 1/3. All right, so this is called the definite integral. It means the area under the curve between these two x values of this function. And the answer is a number. All right, very different from the indefinite integral, whose answer is a function with a plus c. The definite integral, the answer is just a number, which represents the area of this shaded region right there. Generally, the definite integral of some function would be written in this way. The integral from a to b of f of x dx, and this is the area It is this area, all right? The definite integral, the integral from a to b of f of x. It represents this area where you go from x value a over to x value b, and you just draw the region below the curve, bounded by the x-axis and the curve up here, and it's that area right there. All right, how would we actually try to find the area? This is a difficult question. What we're going to talk about today is a strategy for estimating the value of the area. If the area is a weird shape, then it's not clear at all how we would figure out what the actual value of that weird shaped area is. But there is a general procedure that we can use for estimating the area. There's actually a few different strategies that we're going to use to make these estimations, but the simplest of them is using rectangles. Here's the idea. Why don't we just focus for a while on that simple example of y equals x squared and going from 0 to 1. Now, I told you this area ends up equaling 1/3, although there isn't really a good reason for you to believe me at this point, but it is 1/3, just because I know how to do this. Here's the idea. I'm going to divide the interval from 0 to 1 into a bunch of little bitties. I'm going to maybe divide it into 4 pieces. So this is 0.25, this is 0.5, this is 0.75. All right. And above each of those bits, I'm going to draw a rectangle which touches the curve on the right endpoint. All right, and this one goes all the way up there. Okay, we obtain 4 rectangles here, and the area of these 4 rectangles is kind of close to the area of the curved region, right? If I were to find the area of these 4 rectangles and add those together, I would get something that's kind of close to the area of the curved region. It would be an overestimate in this case because you can tell the rectangles are sort of stretching over. They're too big to measure exactly the curved area, but it would be some kind of estimation of the area. That's the idea behind this strategy that we're going to talk about today. Estimating the area using rectangles. We draw rectangles and then add their areas. Adding the areas of the rectangles is easy, right? Just because everybody knows how you find the area of a rectangle. Nobody knows how you find the area of this weird curved shape, but the rectangles are easy enough to add up. And you will get, like I said, an estimation of the area of the curved region. How could you make this estimation more accurate? You could draw more rectangles. This one I used 4 rectangles and the estimation is not terribly accurate, but look what the picture would look like if I used more. How you like those? Here I made 10 little rectangles here, and I think you should agree with me that this is still an overestimation. If you add up the area of all those rectangles, it is still more than the curved area because you can see they're hanging over extra area under the rectangles. But the extent of the hanging over is lesser than over here, right? This one is hanging over quite a bit, whereas this rectangle here on this picture is being broken into smaller pieces and the overhangs are smaller, all right? So the moral of this story is, more rectangles make it more accurate in terms of an estimation of the area. If you want your estimation to be really good, you should use many, many rectangles. Now, it makes it harder to do the computation because you have to add up more areas, but it will be more accurate as an estimation. The number of rectangles that you use is important when you're doing this kind of thing, and we're always going to call that number n. So in this case, this one has n equals 4. That's the number of rectangles. Right? You can see them. 1, 2, 3, 4. And this one, n equals 10. All right? Higher value of n makes it more accurate. Let's try to actually add up these areas of these rectangles. I have 4 rectangles, right? I'll call them 1, 2, 3, 4, right? And, you know, everybody knows the area of a rectangle is the base times the height. So in this case, the rectangle areas, if I add them up, I'm going to add together 4 things, right? Because there are 4 of them. And each one looks like the base times the height. So each rectangle area is the base times the height. And what is the base? Actually, they all have the same width as the base. In this example, the width is 0.25, right? That's how far across each rectangle is. So in this case, the base, actually we have a notation for this also. We call this delta x. You think of this as the amount that the x is changing from one point to the next. And in this example, it is 0.5, 0.25. Right? In between each of those values is a distance of 0.25. And what are the heights? Well, the heights are different between these 4 values. Between these 4 rectangles, the heights are different. How do you figure out what the height is? That's not so hard either. For example, this one has height 1. This one, its height would be whatever that value is, but that value is on the curve, y equals x squared. So this must be 0.75 squared. Can I just say the heights... The bases are all the same. The heights come from the function values. because the height of each rectangle here is determined by the y value where it hits the curve, and where it hits the curve is determined by the formula for the function, whatever the function is. In this case, it's y equal x squared. So my heights in this case, in my example here, the heights are given. The first height is 0.25 squared. The next height is 0.5 squared. The next height is 0.75 squared. And then the last height is 1 squared. All right. So if we want to add them up, what does it look like? I'm going to write 4 things added together because I want to add together these 4 areas. Each one will look like the base, which is 0.25, times the height, which is one of these. It looks like this. Right? I added together each 4 times, and each time what you see is the base width, which is 0.25, times the height, which is given by the values of this function on the curve. All right? One thing that we can do to simplify this very slightly is, because the base is the same every time, you can factor out, in this case, the 0.25. We don't really need the picture anymore. You should still kind of keep in mind that picture, but actually you don't really have to look at the picture to do this at all. This is the same as 0.25 times, and then I see 0.25 squared plus 0.5 squared plus 0.75 squared plus 1 squared. All right? This you can't, actually this is not so hard to compute by hand if you really wanted to, but I put that in my calculator. I got 0.46875. All right? This is an overestimation of the true area. Remember, I told you, just because I said so, the true area in this example is 1/3. This doesn't seem all that unreasonable for it. It's supposed to be an overestimation of a value which is actually equal to 1/3. All right? This is how you add up the rectangle areas. Generally speaking, it looks like like this, right? This was a lot of specifics in this problem, but what would it look like in general if I asked you some different function, perhaps some different interval along the x-axis? You would multiply the delta x out here. That's what this was, the width of each little interval. And then in here, what you see is I'm adding together a bunch of values of the function. I'm taking a bunch of points and plugging them into the function. Really, this is like f of something plus f of the next thing, ending up with f of the last thing. All right? Generally speaking, this is how you're going to do one of these things where you're adding up the rectangle areas. You put the delta x on the outside because that's the base, and then you add together all the heights. And these are the heights. They are determined by values of the function. Okay? The language that you're going to see used to describe exactly what we just did is, it's going to say something like this. What we did was we estimated the area using rectangles on the right endpoints with n equals 4. So rectangles, of course, because that's how we did it. With n equals 4 means 4 rectangles. What about this phrase, on the right endpoints? Rectangles on the right endpoints. This refers to the fact that these rectangles were drawn so that each one touches the curve on its right endpoint. All right? This is the right side of this rectangle. The rectangle on its right side touches the curve. We could also do the same thing, but using the left endpoints. In that case, the picture would look like, using the left endpoints, the picture looks like this. Now we have our rectangles and they touch the curve on the left side. This was kind of a stupid rectangle which has a height 0. That's possible. It's a little weird, but that is what happens sometimes. This is what we would get if we did the rectangles using the left endpoints. Could we compute this answer exactly? Yeah, I think we can. Now, I said before, actually, it's not really helpful to be using the picture. You don't typically have to look at the picture. But can we say, when I use the left rather than the right endpoints, what's different about this? First of all, the delta x is not different, right? I still divided it up into 4 pieces using left endpoints with n equals 4. I suppose I didn't say that, but this is what I meant. Still using 4 rectangles, but use the left endpoints instead of the right endpoints. All right, delta x is the same. What's the difference then? Is there any difference? The difference is we use different values to plug into the function. In this example, the values I plugged in were 0.25, 0.5, 0.75, and 1. But in this example, the four values are over here, right? They are 0, 0.25, 0.5, 0.75. That's the only difference. So otherwise you do all the same stuff. So in this case, the area, I'm going to say, can I say it like this? The area is approximately, remember this is meant to be an approximation of the true area. It is delta x on the outside, which is 0.25, times, I'm going to add together four things. They're just these four numbers instead of those four numbers. That's the only difference. So it's going to be 0 squared plus 0.25 squared plus 0.5 squared plus 0.75 squared. All right. I'm squaring them, remember, because I'm trying to get the heights, which is obtained by plugging into the function, right? The function here is y equals x squared, and so that's why I squared them all. This one, just for fun, I plugged that into my calculator also. I got 0.21875, all right? This now is an underestimation of the true area because you can tell these rectangles are smaller than the true area. All right, so we can do the left endpoint or the right endpoint. It's just a matter, it's almost the same. It's just a matter of which points do you choose to plug into the function. All right, let's try another one. This is very similar. Same function. I'm saying estimate the integral from 0 to 1 of x squared dx. That means the area under the curve from 0 to 1. Using rectangles with n equals 10. This time we got to add together 10 things instead of 4 things. And let's do it first with the left endpoints and then again with the right endpoints. These two answers will be almost the same. Now, it is a real pain to draw this picture with drawing 10 little rectangles. I'm not into that. Actually, it doesn't matter if you know what the graph of the function looks like. You can do this whole thing without looking at the graph. I do find it helpful to just make a little graph. I guess this is more like just a chart of the x values that I'm considering. I'm going x values from 0 to 1. So these are the x values, and we must divide this into 10 pieces. So I'm going to divide it in half. This would be 0.5, and then I got to go. All right, I drew my interval and the subdivisions. And then these are all the x values with which I'm going to start adding together. Now, from the picture, I can tell myself, what is delta x here? Remember, delta x refers to the width of each little sub-interval. In this example, it is 0.1, right? Okay, so this is going to go like all the way out front in front of my answer. And then I'm going to add together a bunch of stuff. So I think we can just do it. Let's say the left endpoints. Remember, my answer always looks like delta x times a bunch of stuff, right? Delta x out here, a bunch of stuff where I have plugging into the function. I'm plugging all these numbers into the function. Actually, not all of them. When I do the left endpoints, I choose the leftmost number every time. So for the left endpoints, I'm going to pick these ones, including the first one, but not including the last one. I'm choosing the left endpoint of every interval. So when I do this using the left endpoints, I get delta x on the outside, which is 0.1, times, maybe I'll write this out in a couple steps, f of 0 plus f of 0.1 plus f of 0.2. You are taking each of these left-hand endpoints and plugging them into the function. Plus, would you mind if I write this dot, dot, dot? I would encourage you to write the dot, dot, dot when you're doing your homework or something. You don't have to write all those little numbers in there. But if you're going to do the dot, 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 that's great. You should give me the last one, though, just so that I know, because it is important that you know where to stop. In this example, you should stop at f of 0.9, all right? This is basically the answer, although you should indicate what this function is. If only for me, when I'm reading your answer on the quiz or something, I want to know that you know what you mean by f. What is the f here? The f is this function. It's the function which we are trying to measure these areas for. So this, my final answer would be 0.10 squared plus 0.1 squared plus 0.2 squared, etc., all the way down to 0.9 squared. There you go. This is the estimation of the area using the left endpoint. I plugged this into my calculator just so we could see, and I got 0.285. That was the left endpoint. Let's do the right endpoint. Can we just say, what's the difference? The difference is almost nothing. It's just when you plug all these numbers in. This time around, I started with 0 and ended with 0.9. When I'm doing the right endpoints, I should start with 0.1 and go all the way to 1. That's the only difference. Everything else is the same. You probably don't really need this, but just so that it's clear, I'm going to write my little interval again. And I choose the right endpoints every time. This one, this one, this one. All the way to the end. All right. These are the numbers that I'm going to plug into the function. So it looks almost exactly like this. Can I just jump straight to this part? 0.1 on the outside, same delta x. That represents the width of each subinterval. And then here, I'm adding them up, but starting at 0.1. All the way up to 1 squared. That's how we do it. This one I plugged into my calculator and I got 0.385. Blah, blah, blah. All right. You will notice these are better estimations than the ones that we got when we used only 4 rectangles. Remember, the true answer is 1/3. So this is quite a bit closer to 1/3 than the first time around. We were getting like 0.48 something for this one, which is not so great. This is quite a bit more accurate, which you would expect because we used higher values of n. Approximate the area under f of x equal e to the x minus 1 from x equal 1 to x equal 3 with n equals 4 using the left endpoints. Are you worried about this e to the x thing? Don't worry about it. Actually, these ones are always going to be easy to do provided that you remember the steps. No matter what this function looks like, you should not be worried ever at all. I'm going to begin by drawing this little chart of the interval. Now this time it goes from 1 to 3. All right. Who knows what the graph looks like? It's not important. You don't need to know what the graph looks like. You just need to chart out what the interval is from 1 to 3. And it says if n equals 4. That means I'm going to divide this region into 4 smaller bits. How about when I want to divide into 4 equal pieces, I'm going to divide it in half first. This would be 2 then, and then divide each of these in half. Midway between 1 and 2 is 1.5. Midway between 2 and 3 is 2.5. All right, I have drawn out my interval, divided it into 4 pieces. Now we can, just by looking at this chart here, can we say what the delta x is? In this example, delta x, this is always the width of the little bitties. And in this case, it is 0.5. All right. Now, this you can usually determine just kind of by common sense by looking at your chart. Although sometimes it can be a little tricky. It will be helpful for you to remember there is a general formula for the delta x that you can use if for whatever reason you can't sort of common sense out the chart here. It's this. The delta x is always equal to b minus a over n, where b and a are these two endpoints. B is the greater one, A is the lesser one. In this example, B minus A over N would equal 3 minus 1 over 4, which is 2 over 4, which is a half, which is what that is. So this is another way that you can figure out what the delta x is if you have a hard time, for whatever reason, if you have a hard time drawing this little chart. Okay, anyway, I think we're ready to proceed, and really there's not much work to be done here. Using the left endpoints, it says, so I'm going to choose these 4 values. These are the ones that get plugged into the function, and I'm going to have delta x in the front. So my answer will be delta x, which is 0.5, times, I plug these 4 values into the function, f of 1 plus f of 1.5 plus f of 2 plus f of 2.5. Right? Don't leave your answer like that because I want to see that you know what the f's mean. The f refers to this function right here. So my final answer will be 0.5 times, and now you plug 1 in here. It will say e to the 1 minus 1. All right. Plus, plug 1.5 in. E to the 1.5 minus 1 plus e to the 2 minus 1 plus e to the 2.5 minus 1. And this is my answer. Of course, I would not expect you to try and simplify that. Without it using a calculator, you can't simplify that. All these e's need to be done on a calculator. Great. All right, let's just do one more. Approximate this integral using n equals 5 and part A, the left endpoints, part B, the right endpoints. Part C, the midpoints. We didn't even talk about that yet. It's not hard to do. We'll get there when we get there. Let's just do the first two first. I am going to, just like before, try to draw a little chart of this interval. The whole interval goes 3 to 4. Using n equals 5 means I divide this up into 5 bits. All right. When you're drawing these little marks, you don't draw 5 marks. You draw 4 marks to make 5 total pieces that you're cutting this thing into. Where exactly do these marks have to be to make it across in 5? Maybe you can just figure that out by common sense. If not, you can always use the old b minus a over n deal, right? Delta x is b minus a over n. This will always work. B and the a are these 2 points, so this would be 4 minus 3 over 5 in this case, which is 1/5. All right, so this is 3 and a fifth, 3 and 2/5, 3 and 3/5, 3 and 4/5, up to 4. In other words, this is 3.2, 3.4, 3.6, 3.8. All right. Great. So the delta x is 0.2. Okay. Let's say our answer. So for part A, using the left endpoints, I'll put the delta x out front, which is 0.2. And now inside parentheses, I'm going to add together the values of the function on the left endpoint. So this would be f of 3 plus f of 3.2 plus f of 3.4 plus f of 3.6 plus f of 3.8. Right? And this is, I don't want to leave it like this. We should say what the f's actually mean. It means this function. So, were you worried about this natural log? I know some people get get nervous in the presence of the natural log. It really doesn't matter at all. All you're going to do is plug the number in. You don't have to take the derivative or the antiderivative or anything. Just plug the number in. F of 3 means ln of 3 cubed, whatever that is. Doesn't matter. Put in your calculator if you want. This is ln 3.2 cubed. ln 3.4 cubed. That's all there is to it. This is the answer using the left endpoints. Okay, using the right endpoints, maybe I'll just squeeze it right in here. Same thing, the only difference is I don't start at 3, I start at 3.2. So this is, all right, that's the right hand endpoints. What about the midpoints? I said do the midpoints. Now, we haven't ever done that before, but don't let that stop you. What does the midpoints mean? You don't have to be a genius to know what that means. The midpoints means the points in the middle. It's these points in the middle. The middles, the midpoints, the middles. That's what it means, the middle points. What is that point in the middle? Well, you got to do a little bit of figuring, I suppose, to figure that out. It's, in this case, between 3 and 3.2 is 3.1, right? This one is 3.3, 3.5, 3.7, 3.9. And when it says use the midpoints, those are the points you use. All of them, all 5 of them. In every case, you're adding together 5 things, right? Because n equals 5. You need to use all the midpoints. Don't try and skip one or skip the last one. No, you use them all. So my answer for part C will be just the same as this, only I'm using those values instead. I'll get 0.2 on the outside and then a bunch of natural logs. ln 3.1 cubed plus ln 3.3 cubed plus. That's how it's done. The midpoints. It's no more difficult than the left or the right.